So we're now going to have a look at example 3 of the ORTools toolbox. In example 2, we reconstructed the parent beta phase from an alpha titanium microstructure. And actually we saw in the orientation relationship fitting program that there were two orientation relationships at work. In this example, we're going to look at both orientation relationships and see how they're reflected in the microstructure. You can find example 3 again on my GitHub page for ORTools right here. And yeah, just download the entire software, and example 3 will be in the main root folder. So with that being said, let's open MATLAB. We have example 3 opened, and I'm going to run through the sections again. Again, if you're doing this the first time, maybe start with example 1, where I'm taking things a little slower and explain more details about the code. So we basically close everything, initialize the folder, we open up mtech, initialize some more folder structure. Then we're going to load in the mtex data set alpha beta titanium. And once we've done that, we calculate the grains for this kind of data set. We do this with a threshold of 3 degrees. And after we're done with calculating the grains, we want to rename the phases and recolor the phases. So here's that dialog. We can rename titanium beta to beta and titanium alpha to alpha. And this time we're just gonna cancel this. Just want to show you that you can do this as well. I would just keep the original color then. So now we have this function set parent grain reconstructor, and here we have to tell the program which is the parent phase, which is the child phase. So we could use either of these two phases, but we could also actually take a phase that's not present in the ABSD data set from a CIF file and use that for doing calculations. Right now we use the parent phase beta and the child phase alpha. After that, we can just do fast plotting again, just to remind you what microstructure we have. So you can again see in this phase map that we almost only have alpha. In fact, it's 99.7% alpha in this microstructure, and there's only a few pixels of beta in the microstructure. And this is the child-child boundary misorientation map. And here you can see that almost all the child boundaries share an orientation, misorientation of around 60 degrees. So now we basically go into the same step that we did before in example 2. We go into this peak fitting program. And what we see plotted here is actually distribution of the parent-child grain boundaries, misorientations. So as you recall, we only have very little parent phase in the microstructure, so the amount of parent-child grain boundaries is very little. Anyway, we can see that we have one main peak here. This one we used before and quite successfully to reconstruct the microstructure, but we also have some not insignificant second peak here. And this time we're going to set the threshold low enough that both of these peaks are going to be fitted. So you can see that they've both been fitted. Now we can choose the R termination according to the maximum value of this distribution. And after this fitting is done, we get to this menu here. So now we can choose if we want to continue working with the first OR or the second OR that has been determined. We can see down here in the command window what these ORs are. We want actually to export both ORs. So we click this. And the OR is of course written into this job kind of object, and usually this job object immediately gives us the misorientation, all these things that are stored in this job object. In this case, since we've exported both ORs, this is now a cell array. So if I write job, you can see that I have two parent grain reconstructors in there instead of just one. So for the first OR, I can do job 1 and get the information about that, and for the second one, I can take job 2. And this is the way we're going to continue this code. So if you want to replicate this example, make sure you export both orientation relationships. Otherwise, you're gonna get an error later on if you use this kind of syntax with curly brackets. One thing we saw here is that this orientation angle between the first orientation relationship and the second one is pretty exactly 30 degrees. So they are quite far away from each other. So now we can actually plot the first and the second orientation relationship next to each other and see how they differ. So let's first start with the inverse pole figures, where we look at the misorientation axis and the disorientation of the orientation relationship with the grain boundaries. So let's now have a look at one figure at a time. So this was the first figure, and we can see this is in the basis of the parent phase. This color axis shows us a disorientation up to 5 degrees. We can see that there's a group of points here that actually agree quite well with this orientation relationship. Recall again, there's only very few parent-child grain boundaries, so this is not going to be a very big area. The majority of parent-child grain boundary points are sitting, or misorientation axis, they're sitting down here and have a quite high disorientation. Yeah, but there seems to be a group where this OR, this first smaller OR, seems to work quite well. Then this is the same plot, now just plotted in the axis of the child grain. And as the last plot, we actually have child-child misorientations. So the majority of misorientations in this microstructure are child-child because we almost only have alpha phase. And we can see where the theoretical misorientation axis of this OR are supposed to be. And we can see it only in this very corner here. We can get some of the points to agree both on the misorientation axis and on the disorientation. So there is few points down here that kind of conform with those OR, but most of them are a very bad fit, as you can see. So we can do the same thing, of course, for the second orientation relationship to see if that gives us a better match with the microstructure that we have. So we're just waiting for those 3 plots to finish, and then we're gonna take them one by one again. So let's start again with the parent to child boundaries in the parent basis. We can now see that the second orientation relationship belongs to this larger group of points here. And we have both the axis lying on the points and a low disorientation. So there seems to be a quite high number of parent-child boundaries that actually match this orientation relationship. And we can see that those points that were in the other earlier highlighted by the other orientation relationship don't fit to this one. That's why they're distinct in the plot. In this kind of distribution plot where we did the fitting earlier. So this is parent to child boundaries again in a child basis, nothing new here. And as the last point, we have the child-child misorientations. So now we can see that we again have 6 misorientation axes here. And in all of these misorientation axes, apart from this one, we seem to have a lot of points scattered around, and they all seem to agree quite well to the orientation relationship. So the disorientation between those grain boundary misorientations and the orientation relationship seem to be quite low around these areas. And this seems to actually cover the majority of points. But we can actually see that there's still 2 regions where the disorientation is quite high, so these don't seem to fit very well to the orientation relationship. But one thing that's maybe important to note is that this orientation relationship also seems to cover the same points that were covered by the first orientation relationship in this corner. What this tells us is actually that these 2 orientation relationships can be distinguished in the parent to child grain boundary misorientations. There are 2 distinct points, but actually that both of these orientation relationships lead down to the same axis angle for the child-child boundaries. So basically, this orientation relationship covers also all the points that were covered by the other orientation relationship and more. So there's a little bit higher credibility for this one. Obviously, it also made the majority of the peaks that we were fitting earlier. So now we can also have a look at the maps as we've done in previous examples. So let's first start with the smaller of the orientation relationships, the one that did not fit that well. And we're going to threshold the color at 5-degree angle to actually highlight how good the fit is. Yeah. So this is the map that we get, and we can clearly see again the prior beta grain boundaries. This seems to work quite well, but also within those beta boundaries where grains should ideally be correlated by an orientation relationship, you can see that there's many boundaries that don't conform very well with this orientation relationship. Interestingly, there is some regions close to the grain boundaries here that seem to work particularly well. So maybe these are just some certain variants that have formed from the grain boundary for which this orientation relationship works pretty good. Let's maybe have a look at the second one so that we can compare those two. So in the second orientation relationship, we can again see these beta boundaries being highlighted by a very high disorientation, as we expect. And within those prior beta boundaries, we can actually see a quite low disorientation, which indicates that our orientation relationship is very well represented in those grains. What's now interesting is, of course, to compare the two. So on the left side, we have the first orientation relationship. On the right side, we have the second one, both with a threshold from 0 to 5. Um, so now we had some areas in the first orientation relationship that actually look quite all right. So just close to some of the prior beta boundaries, there were areas that are well represented. But we can actually see they're just as well represented with the second orientation relationship. So this just seems to be some kind of symmetry coincidence that in a certain combination of variants, this OR shows the same misorientation angle as this orientation relationship. And we saw earlier that both those orientation relationships are very clearly distinguished by a 30-degree orientation. So it kind of makes sense that there's some common ground for those orientation relationships. But in overall, we can see that, yeah, basically everything can be nicely reconstructed with the second orientation relationship, whereas the first one does not really help us in our pursuit to reconstruct things. We can also plot the probability here, but I'm gonna leave that out for now. What we can now do, just as a last point, is we can compute the Burgers orientation relationship, um, which is usually what we expect in the alpha beta titanium system. And then if we see what's the angle or the angular misorientation between the Burgers OR and our second orientation relationship, we can see that we have 0.2 degrees. So we can be quite confident that the second orientation relationship is the Burgers orientation relationship and that we can neglect the first one. I am not sure if the first orientation relationship actually has some kind of physical foundation, because it has been, of course, determined on the basis of very few points. So if anybody knows whether that's a real orientation relationship or not, I'm happy to hear about it in the comments. But apart from that, I think we can just discard the first orientation relationship and see that it's not really valid in this microstructure, or that it's not really useful, at least to pursue in the further calculations. And in this way, you can use the OR peak fitter to look at different orientation relationships. You can then separate those, look at the separate effect of them, and you can actually also now continue doing the reconstruction with one orientation relationship, and then basically to the second reconstruction with a second orientation relationship after that. That's something I'm going to introduce in a later video as well. So bye for now.